Testing 1, 2, 3. Blah, 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 blah. Okay. Hey guys, and welcome back to another video on the channel. In today's video, we're going to be looking at Chemistry Paper 1 for 2020 from the QCAA syllabus. This video is the short response. Now, I'll break this video up into two parts because it's going to get very big very quickly. But pretty much with this one here, this is just for units 3 and 4. You get given this chemistry data book to pretty much answer the questions in. And yeah. If you have any questions about the stuff I look at in this video, please timestamp where you're confused and what question it is, and I'll try my best to answer it in the comments, okay? But otherwise, let's get straight into it. So here, this is where you put your multiple choice instructions, and yeah, we just go all these questions here. Okay, so we'll start with the first one. So, glucose is an example of which type of carbohydrate? So, glucose is what we refer to as a monosaccharide, okay? Which pretty much means a single sugar, okay? Another way you can refer to it is aldose, which is another name for the same thing. So here you literally got to put monosaccharide. I think it's spelled like this. So mono meaning one, and saccharide is just referring to pretty much it as a sugar, I believe, okay? So you can put that, or you could put aldose, okay? And that prefix is referring to the glucose, okay? And that's how you answer that first one. Alright, question B. Starch and cellulose are both polymers of glucose. Compare the structures of starch and cellulose in terms of their glycosidic links. So here we kind of need to know pretty much what they look at. Now, starch and cellulose are what we call polysaccharides. So poly pretty much means more than one sugar. So they're like these really big long chains of, glucose pretty much made together. Now, the only difference between the two of them is what type of glucose is used. So cellulose uses beta glucose and starch uses alpha. So this is pretty much all I remember about these guys, and they're really big chains. Now you've got to remember, you've got to use and compare the glycosidic links. So pretty much where they join up, okay? And they all join usually at a 1,4 glycosidic bond, okay? So pretty much we need to compare the structure. So on your data book, you're given alpha glucose, which is down here. So if we go down here, you're given the cyclic form, okay? And this is alpha glucose, okay? Now, the only difference between this and beta is the OH and the hydrogen are swapped, and this is what we call the carbon one, okay? So what we'll do is we'll just draw pretty much the beta glucose and just see how that looks, okay? So here, I'll just do my best to draw it. So I've got it drawn here. So here you go draw it like this. So oxygen. I'll just draw the structure at the moment, like this, and see how we go. Alright, so here, this is beta glucose. Well, actually, no, that's, well, I thought I was drawing galactose for a second. No, OH, H, then that one is H, OH, then that's OH, H, and then this one has H, and then CH2OH. So this is glucose beta, because these have been swapped around. So look how this is different to the alpha, that's just been swapped around, okay? And they form it at 1,4 glycosidic bond. So what that means is referring to the carbon, okay? So pretty much here, if you add two of them together, this is the first carbon, okay? So that's carbon 1, carbon 2, 3, 4, okay? So what's going to happen is when they join up, this hydrogen is going to pop off pretty much, okay? So if I were to, there's no way I can really condense this, so I'll try and draw it a little bit better. If you were to draw them together, so I'll just draw it like this. So we'll have, we'll go like this, oxygen, OH, H, like this. So it still has the same structure here. The only thing here is the hydrogen pops off here. So you have an oxygen here, hydrogen, OH. Then you have, no, you still have the hydrogen there because just the OH one pops off. And then you'll have the CH2. I'm just making sure I draw the diagram correctly because I've got it drawn here. I don't want to draw it incorrectly. And then you got the hydrogen. So pretty much this is one glucose, but all that's happened is this hydrogen's popped off. Now, when it forms with the bond here, this OH is going to pop off. So I'm going to draw the exact same molecule, except just down here. So this is joined up here, And I'll just draw the structure. So we'll have the oxygen here. So this is carbon 1 here. And then I'll just draw the general structure like this. So you just draw the same thing. So that's going to have the hydrogen down below. Then literally the exact same structure. OH, H, and then that would have OH, H, and then that one would just have H, and then CH2OH. So if I were to rub this out, this is what cellulose would look like. So this is just two of them joined together, but this is an example. Oh, and there's also water as well. Okay. So this is pretty much a huge structure of this. So imagine n lots of this. This is what cellulose looks like. So this is the 4, and that's the 1. So that's what they mean by a 1,4 glycosidic bond. Okay. So when responding to this question, I would actually physically refer to pretty much this bond here, and actually I would draw a picture as well. Now, if you want to do, so that's cellulose. If you want to do literally starch, all you got to do is you just got to flip these guys around and do the same thing, but make sure you include the water as well, because that will always be a part of it. Okay, so all you do is flip those upside down, and just draw the structure of this guy here. Okay, where pretty much this it would actually look more so like the other way, because they're kind of symmetrical on each side. As you can see here and here, symmetrical. So it would look more like a straight chain rather than on a diagonal like this. But all you got to do is just compare the difference between the two of them. So I would mention those are flipped, and they still have that 1,4 glycosidic bond. Okay. And yeah, I think that's all the question is asking. So yeah, just a polysaccharide, because you could have n lots of it. So it's just not 2. I just drew 2, just an example to show you where the bonds were. Okay, but that's how you would answer the first one. Okay. Alrighty, question 20. Again, if you have any questions about this one here, leave something in the comments, because I'm not actually going to write physical response to it, because I think my verbal explanation is enough. Because yeah, writing like this isn't ideal. Okay. Alrighty, so question 22. The structure of, I don't know how to pronounce that word, phenol red, when it's either an acidic or a basic solution are shown in the equation. Okay, so straight away we have an equilibrium system on our hands. Okay, so in equilibrium we have probably a weak acid, because they mention acidic or basic solution. Okay, identify the species that acts as the conjugate base by circling in the equation. Okay, so pretty much an acid donates a hydrogen. Okay, so the only difference between these two structures is here and here. This has donated the hydrogen and has formed a double bond there. Okay, which makes this the acid, which implies this must be the conjugate base. Okay, and that's it, because acid makes the conjugate base, vice versa. Okay, and that's how you answer that first question. Okay, question B. A solution of phenol red at equilibrium and 50 degrees Celsius was found to contain 2.0 times 10 to the negative 4 moles of the conjugate base and 0.03 molar of the acid. Determine the pKa value for the system, assuming that all protons present come from the dissociation of the acid. Okay, so with this guy here, pretty much we have an acid, so just say AH, which represents this guy up here, because I'm not going to draw that whole chemical structure. It pretty much goes like this, back and forth. It produces the conjugate base and protons, aka hydrogen ions. Okay. Now pKa. pKa is negative log 10 of your Ka value. Your Ka value is your equilibrium constant for a weak acid, because that's what we have here. Okay, a weak acid. It's going back and forth because it hasn't fully dissociated, because you still have some of the acid and conjugate base. Okay, but this is generally how we could write it. Now, the Ka, like a normal equilibrium system, will be the products divided by the reactants. Okay, now we're assuming it's a 1:1:1 ratio. Okay, now we've been told that there is this much of the conjugate base. So A negative, which is your conjugate base, is 2 times 10 to the negative 4 molar. Okay. Now we've also been told the acid, HA, has 0.034 molar of the acid. Now I know what you're thinking. How are we going to work out how much hydrogen or protons there are, given we haven't been told anything? Because your Ka is going to be your conjugate base times your hydrogen ions over the acid, okay? When this is how we can work it out. When it dissociates, it's a 1-to-1 ratio. So if we know how much of this goes to that, that means the amount of this must be exactly the amount of this, because of the 1-to-1 ratio using stoichiometry, okay? So because of that, we also know that the hydrogen ions must be equal to how much of this we have, okay? So by definition, we've got pretty much 2 lots of that, okay? So the amount of hydrogen ions is going to be 2 times 10 to the negative 4 molar, okay? And that's how you do it, okay? So now we've actually got all these values at equilibrium. Because they've said they're at equilibrium, we can just chuck them into this equation here and calculate it, okay? So scroll down. So Ka will be 2 times 10 to the negative 4 times by 2 times 10 to the negative 4 divided by 0.034, and we'll chuck that into our calculator. So we do that. I'll just do it now. 2 times 10 to the negative 4 and then 0.034. We should get about 1.17, so 1.17 times 10 to the negative 6. So because it's quite small, it pretty much means that there's a significantly amount more of the acid than anything else. Alright, so now we've got that value, so let's just rub this stuff out because we need it to work out the pKa. So pKa is again negative log 10 of the Ka, so it's going to be negative log 10 of this value here, so 1.17 times 10 to the negative 6, and you chuck that into your calculator. You wouldn't be able to do this by hand in chemistry. 1.17 times 10 to the negative 6, so you should get about 5.93. Again, they said 2 significant figures, so I'm just going to put 5.93. Again, there will be rounding issues because I rounded numbers, so it might not be exactly the same, but it'll be around that value. Okay, and that's how you do this question here. It's quite tricky-ish because of the stoichiometry, but as long as you know, alright, that's a 1-to-1 ratio, this amount must equal your hydrogen ions then. That's the only way you can do this problem. Okay, question C. So, explain the relationship between the pH range of phentyl red and its pKa value. Okay, this one is actually quite tricky, okay? Because what we actually need is actually some stuff not really taught much. We need a special equation. So I'll just change the color. So the pKa isn't just negative log 10 of pretty much the Ka. If you did some rearranging, you also get this. So pKa is equal to pH minus log 10 of your conjugate base over your acid, okay? If you have this structure here, okay? So acid produces back and forth conjugate base and protons, okay? Now, there's a couple things we have to explain here. If we want to explain the relationship between these guys here, okay? Now, pH is a measure of how acidic something is, okay? So this value is going to be very important depending on pretty much how much concentration we have here, okay? Now, it all comes down to this guy here, okay? If you log a number less than 1, it will be negative, okay? So if we have, let's say the pH is less than the pKa, that pretty much implies that we're going to have more of the conjugate base, actually less than, more of the acid and less of the conjugate base. So we're actually going to have this, okay? And I'll explain to you why. The reason why the pH, if the pH was less than the pKa, the reason why this is true is because, alright, if there's more acid, that means there's a bigger number on the bottom here, which means this whole number is a decimal, which means this whole number will be positive because log of a number less than 1 is negative, times by negative just gives you a whole number here. So you'll get like, let's say pKa equals pH, let's say in this case here plus 1, okay? That means the pKa is bigger than pH because your pKa is your pH plus a number. So that's where we get this idea from, okay? Now, likewise, if the pH is greater than the pKa, that implies that there's more conjugate base than the acid. Because if there's more conjugate base, this number here is going to be bigger than 1, which basically means this whole thing would be negative, which means your pKa would be your pH subtract a value here, implying pretty much your pH is larger. Okay, now that's tricky to do and explain if you don't have this equation. So remembering this equation is actually quite important when explaining relationships here. So when it says explain the relationship between pH range and fentanyl red and its pKa value, well, this is what we're going to do. And yeah, that's all pretty much we've got to explain here. Now, if it's more acidic, so if we think of the pH scale as well, the lower numbers, the more acidic it is. So like 1 is very acidic. The higher numbers, the more basic it is. You can also think of it like the rainbow as well. So if it's very low numbers, that's where red starts, and the higher it goes, that's where the lighter colors like blue and green stuff go. Okay, so I would say if the pKa is less than the pH, then we're going to have pretty much a more basic solution potentially. If the pH is greater than pKa, we're going to have a more acidic solution. So that's where you would go with colors. Now, all they said is explain the relationship between the pH range and the pKa. You could go into more details on the colors, but I think this is all you should need. Okay? But yeah, I would say I'll probably give myself 2 marks. Again, I don't know what the answer is. I'll go back and check it. If there's any questions about this one here, leave something in the comments and I'll try my best to answer it. But I feel like if you mention the colors here, as long as there's stuff here as well, you might be able to get 3. But yeah, okay. Alright, so question 23. So this will probably be the last. Oh, actually, we could probably do. How many questions do we have in this exam? Alright, we'll probably do. Yeah, we'll probably do 2 more, and then we'll do the rest in the next video because we don't want a really big video. Right, so question 23. Identify the products of electrolysis of molten sodium chloride and then little I dilute aqueous sodium chloride solution. Okay, so the difference between these guys here is that the first one is just pretty much sodium and chloride. This one is basically a very small amount of sodium chloride with an aqueous solution, so meaning there's a lot of water. So the answers between these two are actually going to be a little bit different. Okay. Now with electrolysis, while sodium and chloride are opposite, well, so pretty much sodium likes to lose its electrons, so it typically turns into this ion, just a normal chemistry. And chlorine typically turns as Cl-, it gains electrons, it rips things off. However, in electrolysis, we are doing to the opposite of what happens in a chemical bond because we are forcing the flow of an electrons using a circuit. Okay, so in electrolysis, rather than this happening, the sodium is actually going to be gaining electrons because you're going to have Na plus the electron to produce Na. And here you'll have also, you'll have, oh, what was it? So Cl2, I think it's this equation. You'll have the chloride ion turn into this. So it's actually going to lose electrons with electrolysis because you're pumping electrons through a circuit, okay? So what that means is pretty much your sodium is going to be at the cathode, okay? And your chlorine is going to be at the anode, okay? So you're going to produce sodium, solid, and you're going to produce chlorine, gas, for the first one, okay? Now with this one here, in a dilute I can never pronounce that word, sodium chloride solution, you have a very small amount of those two elements. You have majority water. Okay, so this is another word for brine, which is pretty much it's just like a weak version of NaCl2 with water, pretty much. Okay, so in this one here, both H plus and Na plus are attracted to the cathode. However, H plus is more likely to be reduced because H has a lower reduction potential than the sodium. So one of the products you're going to have from electrolysis is going to be hydrogen. Okay. Now it won't be the ion, it will be the gas at H2. Okay. Now because it's a low amount, because they said dilute, because it's a low amount of sodium chloride, most people would also say chlorine would be a gas as well. However, it won't be, because there's a very low amount of it. From the water, actually oxygen gas will be produced. So the correct answers with this wording here would just be the hydrogen and the oxygen. If they didn't have this word here, it would be hydrogen and chlorine though. Okay, but because of that word there, the correct answer is going to be hydrogen and oxygen, I believe. Okay, hopefully we got that right. If you have any questions about that, please let me know. I didn't write a lot of that down because there wasn't much writing space and it is only one mark, but I'm explaining my logic behind it. Okay. Oh, I think B is going to explain how this works as well. Okay, so explain how the nature of electrolyte affects the products generated when a dilute. Okay, so it's literally just asking us to go into detail about this guy here. Okay, so pretty much when we have this thing going on, so we have Na plus, it will gain an electron pretty much. Okay, so you'll have pretty much precipitant still. And then you'll pretty much also have the chlorine as well. So we've got these two reactions going on, but you've also got a lot of water involved. Okay, now both the H plus and the Na plus will be attracted to the cathode. Like I said before, majority, I think that's how you spell majority, of it will be hydrogen, because what was it? Hydrogen, I'll just go H, has a lower reduction potential than sodium. So that's why we'll have a significantly more amount of hydrogen than sodium. And like I said before, with the chlorine and oxygen, because there's going to be a low amount of this and there's more water, most of the products will be oxygen, which I think I've already explained pretty much in detail. So Cl2 will be produced, however, the dilution O2 will be produced significantly more. Okay. Again, if you have any questions about this one here, leave something in the comments and I'll try my best to answer it. Okay. Let's go into this one. So I think this will be the last one I do for this video, and then I'll make a separate video for the rest of the questions. Okay, so back to equilibrium. So this table shows the effective temperature of pH on pure water. Okay. So analyze the data to explain whether self-ionization of water is endothermic or exothermic. Explain your reasoning. Okay, so we now understand what endothermic and exothermic is. So endothermic means it needs energy to happen. So you have pretty much, well, let's draw an equation for this. So we have H2O, which breaks down into H plus and OH. Now if it's endothermic, you need energy, so heat, to cause it to go forward. If it's exothermic, you get energy as a product. So energy would be on this side of the equation. Okay, that's the difference between these two terms. Now we can only really examine that via the relationship between the pH and temperature, because the reason why pH is involved is because that's related directly to H plus and indirectly related to the OH. Okay, so as your pH, so as pH decreases, the temperature increases. Okay, so if that's true, so if we have pH decreasing, that means the H plus is increasing indirectly. And we'll write this as well. So temperature goes up, pH decreases, which means H plus is increasing. So pretty much when we add energy, it's going to shift left to right to produce more of that. So left to right. Okay. So if you're adding energy and it's going to go left to right, that means there's already energy on this side, because Le Chalier's principle says if you add anything to a system in equilibrium, it will shift back to equilibrium. So if you're adding additional energy and shifting from this side to that side, that means there's already energy over here. So if it's endothermic, there's energy here. So let's see if this works. So if there's heat plus water produces this, and I add energy via Le Chalais principle, I'm adding more reactants, aka heat. It's going to counterintuit that and go and shift it from left to right to balance it out. So via this here, if the pH decreases, the H plus increases while the temperature goes up and goes left to right, I'm going to say it's endothermic. Okay? So you need energy to produce that. So the delta H will be positive. Okay? Which is like your joules. Alright. Calculate the kW of pure water at 50 degrees. Show you're working. So you got to use this information here. Okay? Now we got to understand. Alright. kW. Formulas for kW. It's like a constant between your how much protons and OH there is, I'm pretty sure, but I think they've got a nice formula here for it as well. Here we go. So they've got it here, but that's only true for that Kelvin. So I think that's 25 degrees. Hold on, so 298 minus 273, yeah, that's for 25 degrees. We want it for 50 degrees. We're gonna need, not that this expression here, so H plus times OH, because we're dealing with that up here. So I'll write this here. So kW is H plus times by your OH. Okay. There will be some people that put this constant as their answer, but that's not true because that's a different temperature. Okay. All right. So we've got the pH at 50 degrees. So we know the pH is 6.63, I think. I'll double check. Yep. And we also know pH is negative log 10 of the ion concentration. Okay. Now, you've pretty much just got to rearrange this to get H plus by itself. So H plus, using your log law, will be 10 to the power of negative pH. So we have H plus is going to be 10 to the negative 6.63. That's how much ion concentration we have. Now, how are we going to work out the OH? We've got to look at this equation here. So water produces H plus and OH. It's a 1-to-1-to-1 ratio, meaning the amount of H plus will be the same amount as OH. Okay, so we know directly that OH is going to be the same amount because it's a 1-to-1-to-1 ratio. Okay. All right. So now we know that we can work out kW because we know the concentrations of both of these ions. Yeah. So kW will be just this number squared. Alright, so we'll check that into our calculator. So 10 to the power of negative 6.63. I'll go squared. Produces, you should get about 5.49 times 10 to the negative 14. Now they said the three significant figures. So go 5.495. Oh, actually no. Significant figures, never mind, not decimals. So 5.49 times 10 to the negative 14. And I'm pretty sure it's unitless. Oh, mole squared. I'm not sure what that is, actually. How terrible is that? I'll just leave it like that, okay? I don't think you'll get marked down in this case here. But usually you put units. Alright. Yeah, well, if you have any questions about these ones we've done here, leave something in the comments. I will do the rest of these questions in the next video, just because the video is going to be half an hour already, okay? Alright, I'll see you in the next one. See ya.